I'm Antonio Sala, and in this video we are going to draw some conclusions on the needed complexity of the model in this heat exchanger case study. In a series of videos, we have discussed a lot of models for this tubular heater we may see down there, from partial differential equations to first order or even static approximations. So if we ask a physicist, he would say that our proposals are just simplistic and there are many other things to take into consideration to get an accurate model of this thing. Turbulence, Navier-Stokes, partial differential equations for heat conduction. However, if this is just a part of something that fills a tank with hot water and we ask the technician what model we need to operate this, then he would just say that, for every kilowatt you increase 12 degrees Celsius the water temperature. So we have just a proportionality. Then, engineers, we are in the middle ground of all that, kind of uncomfortable situation, because physicists would say that our tools are too simplistic, and technicians and users will say that our tools are too complicated. So what can we do? Well, we need sensible proposals depending on the application. Let us review that discussion. As I said, we reviewed a lot of models in a series of previous videos. The most complex one is the nonlinear partial differential equation that we get here as the root of everything. Of course, more complex versions of this can arise, okay? But let us stop here. It's nonlinear because we have products of flow and temperature derivatives. So we have the most complex possibility here, and then we have the simplest possibility in which, making some derivations, we can write kind of this thing. We have the inlet temperature times certain gain and the heating power times another gain, in which those gains depend on some physical parameters and importantly the flow. So we get this kind of two gains, flow dependent perhaps. Temperature increases 12 degrees per kilowatt. We also saw a lot of intermediate models. First order approximations doing an energy balance, and the energy balance was made on an average temperature that depends on the value of some beta, and we gave several options for that beta, the exact one being something related to the solutions of the partial differential equation. But okay, so we have like first order approximations, and we also have finite element models in which I divide this thing in many smaller tubular heat exchangers, and I get an order 2, order 3, order 100 description as an approximation of a PDE. So with one element I get this, with 1000 elements I am very close to the PDE, and with, let's say, 0 elements, no dynamics, I get the static model. And then also, because we have products of flows and temperature or its derivatives, we have linearized versions of all this in order to do linear simulation for small flow increments, both diagrams, Padé approximations of delays. So this is kind of daunting. I mean, even for this relatively simple stuff, we are not doing any, computational fluid dynamics here. It's the sort of simplest partial differential equation we have. We get all these modeling options. What happens if we choose an excessive model complexity? Well, we have a higher computational cost. I mean, simulating an order 100 system is significantly slower than simulating a first order system. Then we need to deal with a trade-off between accuracy and computing time. This kind of complex models and simulations need staff with a higher qualification to understand what we are doing. Finite element, Runge-Kutta stiff integration. So the usage of these high-order models is expensive in man-hours and computers. Also, the resulting controllers with these high-order models, PDEs or, order 1000, okay, many control design techniques result in high-order controllers. It's a sort of unbelievable that we propose an order 1000 controller. In fact, numerical accuracy of the matrix computations to compute, pole placements, observers, whatever, maybe render those computations useless, accumulating numerical errors. And even if they work, a technician controls this thing with an all or nothing controller. If the water is cold, switch the heater on. So how the hell we are discussing using a model with 1000 states? Are you crazy? Okay, an intermediate setup is using a high order nonlinear simulation to optimize fixed structure controllers, say a PID. So we can have a performance measure and test a few hundreds of PID gains by simulating in the nonlinear finite element stuff, okay? This is reasonable in many technological situations. If you have a very good nonlinear model which does not take 2 weeks of supercomputer to simulate, then maybe you can optimize a PID controller based on repeated simulations. But okay, as a conclusion, excessive model complexity and excessive controller complexity is something that does not smell well. People in industrial practice do things in a much simpler way. And in fact, one of the reasons people do not rely in the solutions with very complex models is because in those models there is a lot of uncertainty. Imagine that our tank is not exactly tubular. You get this elongated but not exactly a pipe geometry. So we'll have some turbulence over there, which is not contemplated in the PDE formula. We need more complex PDEs. We need computational fluid dynamics, Reynolds number, and the like. But also, maybe the thermal conduction coefficient, I see that it is 300, but it is 400. Or it is 200 because I have some kind of fouling deposits in the pipe with time. So I have uncertainty in this heating coefficient. Also, we disregarded the heat capacity of the pipe, and in some cases this pipe may have, fins, a particular geometry. So maybe we should add Navier-Stokes, computational fluid dynamics in here, and thermal conduction PDEs. Wow, so complicated. And uncertain heat transfer coefficients. And we also may have a thermocouple, maybe protected with some coating, if this liquid is, let's say, a corrosive acid. So maybe the time it takes for this sensor to get an accurate temperature reading, this sensor bandwidth, is of the order of the residence time of the fluid here. So this is another difficulty. With all those uncertain stuff and simplifications arising even in what we thought a complex model, but it's not complex enough. So what is the use of simulating a 1000th order if we know that there are a lot of things that we did not consider in this PDE? Uncertainty in this kappa, we have uncertainty in my temperature measurements. So, are you sure that using a 1000th order model is really worth it because of all these things? Well, the conclusion of this is that it may be of no practical use if compared to the partial differential equation. A first order simple model had an 8% error, let's say, but we could reduce it to 1% error if I increase the order. But okay, if other sources of error amount to, let's say, 32% of error, then it's kind of useless to enter into these problems just to reduce the error from 40% to 35%. So we need to think if complicated the model will add development cost to my engineering workflow, and maybe it will not yield any tangible improvement in the performance of my final temperature control or chemical reaction engineering application. So I need to complicate my model only if I expect a noticeable performance improvement. With these ideas in mind, let us give, let's say, some very crude rules of thumb on which complication of this model we should use. Of course, if we believe that the error due to, turbulence and steering and the heat capacity and the conductions of all this is small enough to think that our choice between all these families of models will be really relevant to significantly improve the accuracy of our predictions. Then, if we think so, okay, the basic idea is the residence time, washout time, the time the fluid entering here takes to completely wipe whatever initial state we have there. Then let us imagine a range of applications. Say that we are heating some fluid that is going to be stored in a buffer tank, and we output then that fluid at a given temperature, for instance. So imagine that in my particular application, this is a very big tank, and the residence time here is 1 hour, but the residence time in my heat exchanger is 20 seconds. I heat the water here, and then it goes to a very big tank in which I am storing all the fluid that takes 1 hour to pass through. Okay, then in that case, considering the dynamics of this is nonsense. Whatever happens in 20 seconds will be filtered out with this 1 hour of mixing and reaching another thermal equilibrium. So in that case, I would use just the static model, saying that, okay, each kilowatt hits 12 degrees, and due to thermal losses, inlet temperature increments get multiplied by 0.9. So that kind of proportionalities, maybe, taking into account possible flow variations. Then, as I said, that kind of proportionalities will be the only thing to be used in this 1 hour of mixing application. So if the residence time is more than 5 times smaller than the time constants of the system in which this fluid is going to land, say if the residence time is less than 1/10, 1/15 of the settling time of the overall application, then okay, just use static model. In fact, it's important to say that it is the most frequent case, maybe in applications. When you study undergraduate heat exchanger, you do some logarithmic mean temperature difference formula, and you get these static gains. So with those static gains, you can operate a chemical plant with that heat exchanger if the residence time is in seconds and your storage tanks and chemical reactions have residence times in the range of hours. So as I said, in most applications, you will be dealing with this in practice. Okay, but we are control freaks, let's say, and we think that, okay, we need to have tools for more stringent performance specifications. So we may have a second situation in which, let's say, instead of 1 hour, this is a very small tank in which the residence time is 2 minutes. Okay, then things that take 20 seconds are not so negligible. And then in that case, let's say, if we have a residence time that is 1/8, 1/7 or something in this range of the settling time of your intended temperature control application, then okay, maybe we should use, let's say, first order models. So we have kind of a pole introducing some of the dynamics of this transport phenomena and somehow simplified, but accurate enough to improve over an assumption of, let's say, instant heating. Well, good, that would be this second option of modeling complexity. Last, if this buffer tank is even smaller or even, on the verge of non-existing, so residence time here is again another, let's say, 20 seconds. Well, in that case, dynamics here is important, and then I need to use higher order models or even, approximations with time delay, say controllers with a so-called Smith predictor. If I need to add here a temperature transducer, temperature control application, and then decide the heating power, and I want a settling time of 40 seconds, 50 seconds, or on that range, then I need to take into account the delay or a PADE or finite element high order approximation to that, because otherwise my computations in simulation will be very different to my practical performance. But as we say, and we conclude with this here, there is a wide range of model complexity for this physical system. And in fact, if we ask a physicist, he would tell us that even our most complex model is too simple to be true. But we engineers must abandon the hope of having the true model. We just need a good enough model for our application, and for the same physical system, depending on what it is a subsystem of and the performance requirements, we may be happy with a static gain proportionality, or maybe we need the first order approximation, or a fifth order approximation, or a 1000th order approximation. But what we need to understand is that complicating the number of finite element accuracy of this tubular heat exchanger model will not improve anything regarding this unmodeled dynamics and parametric uncertainty and sensor bandwidth issues. So considering this and the actual bandwidth from seconds to hours of my target applications, we need to be smart enough to provide the right model complexity for each use case. Good, we finish with this. Thanks for watching.